Let's move on to example 2. So let's apply Euclid's algorithm to some of the problems from our last lesson. It asks us in the first part, what is the greatest common factor of 30 and 50? Now, we could also use prime factorization. Let's take a minute and review that there. Let's go 30 and 50. 30 can be multiplied or gotten by multiplying 2 times 10, where 2 is prime, and 10 can be broken down into 2 times 5, both prime. 50 is 5 times 10, where 5 is prime, and 10 can be broken down into 2 times 5. And then if we make our Venn diagram, where this circle is 30 and this circle is 50, they both share a 2. 30 has a 2, but the 50 doesn't. They both share a 5, and the 50 has a 5, but the 30 doesn't. If we multiply those shared prime factors together, we get a greatest common factor of 10. Now let's try using Euclid's algorithm. We should end up with the greatest common factor of 10. We take the larger number and divide it by the smaller number, 50 divided by 30. It goes in there one time, subtract. I don't have 0 as a remainder, so I'm going to set up another division problem where the remainder is the new divisor and the old divisor is the new dividend. 20 goes in there one time, subtract. Still do not have a remainder of 0. So I repeat. Now 10 goes in there twice. Now I have my remainder of 0. What's the final divisor? 10. That's the greatest common factor. Let's try it with the next one here. It says use Euclid's algorithm to find the greatest common factor of 30 and 45. Larger number divided by the smaller number. Do I have a remainder of 0? No. So repeat. Making the remainder the divisor and the old divisor the new dividend. Goes in there twice. Do I have a remainder of 0? Yes. What's the final divisor? 15. So the greatest common factor of 30 and 45 is 15. We found that by using Euclid's algorithm. Make sure that you guys don't get Euclid's algorithm confused with the division algorithm. This is used to find the greatest common factor, not to divide a number into another number.